We've seen 5 quantities since we started talking about kinematics. Distance, how far an object has moved, is a scalar. Position, where an object is a vector. Displacement, which is the change in position, is also a vector. Time, which we didn't really give a definition for time because there isn't really a good one, it's a scalar as well. Yesterday we learned about speed and velocity, how fast an object moves, the rate of change of position. Speed was a scalar, velocity was a vector. Today we're going to learn about acceleration. Acceleration is the rate of change of velocity Velocity was the rate of change of position, how quickly the position is changing. Acceleration is the rate of change of velocity, how quickly the velocity changes. The symbol for acceleration is A. It has a little half arrow over top of it. And that means, of course, that acceleration is a vector. There is a direction associated with acceleration because there's a direction associated with velocity. Now, because it's the rate of change of velocity, the units are meters per second, but we usually just write that rather than meters per second as meters per second squared. It ends up being the same thing, just looks a little tidier when we write it this way. And we can have a positive acceleration or negative acceleration. Acceleration will be positive if an object speeds up. In the positive direction. Acceleration is also positive if an object slows down in the negative direction. So let me give you an example to describe both of these here. If I'm walking to the right is a positive direction. If I'm walking to the right and I'm speeding up to the right, then my acceleration is considered to be a positive value. But if I'm walking to the left, and the left is considered to be a negative direction, if I'm walking to the left and I'm slowing down, then that's also considered to be a positive acceleration. Now, when do you have a negative acceleration? Well, you can probably figure this one out yourself, but we have a negative acceleration in 2 scenarios. One where we slow down in the positive direction, and where we speed up in the positive direction, that's a positive acceleration. We slow down in the positive direction, that's a negative acceleration. Can you imagine the last one here? When do we have another negative acceleration? Well, if we speed up in the negative direction. Let me give an example of each of these. If I take a rock and I drop it from the top of a building, it's going to fall downwards. It's going to accelerate down and speed up downward. In fact, it's going to speed up downward at a rate, an acceleration of 9.81 meters per second squared. We would consider that, however, to be a negative value because it's speeding up in the negative direction, speeding up as it falls downward. Now, on the other hand, if I throw the rock up from the ground into the air, then that rock is going to slow down. It's going upwards. It's moving up, but it's slowing down. If it's slowing down in the upward direction or slowing down in the positive direction, then that's also considered to be a negative acceleration. When we're dealing with gravity, when we drop an object or we throw an object into the air and it's under the influence of just gravity and no other forces, then we say the acceleration is always negative. In fact, the acceleration is always negative 9.81 meters per second squared. Remember that. Some problems that we are going to see here today involve acceleration of a car, or acceleration of a person, or acceleration of a ball as it rolls along a hill. But some problems we're going to see involve an object rising or falling under the influence of just gravity. If that's the case, for those problems and those problems only, the acceleration will be, for all of those problems, negative 9.81. It doesn't matter whether it's rising up into the air or falling down. It'll be negative 9.81 meters per second squared. Now, we have one equation, v is equal to delta d over delta t. Today we're going to learn 5 more equations. The first equation that we use for acceleration looks like this. A is equal to delta v over delta t. This is really just the definition of acceleration. Remember we said it was the rate of change of velocity. Change in velocity is on the top. Because it's a rate, time is on the bottom. The rate of change of velocity. Another equation that we're allowed to use here, d, delta d, that's displacement, is equal to vi plus vf over 2 times t. Initial velocity plus final velocity over 2 times the time interval. Another one, we have d is equal to vi t plus 1/2 a t squared. This is an ugly looking one. Displacement is equal to initial velocity times the time plus 1/2 of the acceleration times the time squared. Now be careful when you sub in the acceleration here. Sometimes the acceleration is going to be a positive value. It's going to be a negative value. Go back to your notes to determine when it's going to be a positive value and a negative value. Next one. Well, this one we're going to say d is equal to vft minus 1/2 a t squared. It's almost the same as the last one. A little bit different though. Starts off as displacement is equal to final velocity times the time, and then it's a minus 1/2 times the acceleration times time squared. And then finally the last one. The last one is vf squared is equal to vi squared plus 2 times a times d. Now notice something subtle here. This is not final velocity squared. This is final speed squared. Notice there's no vector sign over top of it. That means it's final speed squared. If we solve for VF, we're not going to get the direction here. We're just going to get the magnitude. VF squared is equal to VI squared, initial speed squared, plus 2 times the acceleration times the displacement. Now, when we see a problem that involves acceleration, we can use any of these equations. It doesn't matter which one we try first. If we happen to write down our givens and we find that we think that our givens are going to match the third one, then we try the third one. If it doesn't work, then we try the second one or the fourth one. All of these equations are valid every time you have an acceleration. If you try one of them, you won't get the wrong answer. Worst case scenario is you just won't get an answer. Try another one. What I don't want you to do, though, when you have an acceleration, is to use the equation that you learned earlier this week. This equation is only valid, you'll remember, for constant or average speed or velocity. I like to call this one my group A equation, my group A. Group A is valid when we have constant or average velocity. I like to call these ones my group B equations. These are valid whenever we have an acceleration. So, if you get a problem like you've gotten in the last couple of days that involves just a constant velocity, use group A, v equals delta d over delta t, just like you have over the last couple of days. If you have a problem involving acceleration, where an object is speeding up or slowing down, then use group B, one of those acceleration equations. Try one of them. If it doesn't work, try another one. Now these equations can be a little bit ugly rearranging. Uglier than the equation v equals d over t that we've already learned how to rearrange. I want to spend a few minutes just rearranging a couple of these, going through the steps, and then hopefully you can transfer those steps to the other equations that you might need to rearrange. Let's take a look at this one first. D is equal to VIT plus 1/2 a t squared. Let's solve for VI. Let's solve for VI, the initial velocity. Here's the rules. You want to get rid of what is not attached to what you're solving for. We're solving for VI. What is not attached to VI? 1/2 AT squared. Let's get rid of 1/2 AT squared because we want to get rid of what's not attached. Now, 1/2 AT squared is added to VIT, so we're going to take that over to the other side by subtracting. Becomes D is equal to VIT, it becomes D minus 1/2 AT squared is equal to VIT. Notice I took that entire term over to the other side by subtracting. Why? Because that entire term was added to VIT. If you got something that's not attached, take it over to the other side by doing the opposite. Now I'm still solving for VI. Now I'm going to get rid of what is attached. What is attached to the VI? It's T. T is attached. So now I'm going to take T over to the other side. Well, look, it's multiplied by VI, so I'm going to take it to the other side by dividing. It becomes D minus 1/2 AT squared divided by delta T. There's my equation. Looks kind of ugly, but it works. D minus 1/2 AT squared over T equals VI. So remember, get rid of what's not attached. In this case, it would be the 1/2 AT squared. Take it to the other side by subtracting because it's added to the VIT. Then get rid of what is attached. What is attached to the VI? Well, it's delta T. It's multiplied by VI, so let's take it over to the other side by dividing. Let's take a look at that same equation. This time let's rearrange for A, the acceleration. Let me write that down again. D is equal to VI times T plus 1/2 A times T squared. Remember, this time we're solving for A. Remember what the rule is. Get rid of what is not attached. What's not attached here to the A? Well, that would be VIT. It's added to the 1/2 AT squared, so let's take it to the other side by subtracting. I get D minus VIT. I took the entire term VIT over to the other side by subtracting because it was added to the 1/2 AT squared. We're left on the right-hand side with 1/2 AT squared. We're still solving for A. Let's take what is attached now over to the other side. That's going to be the 1/2 in the T squared. Let's take that over by dividing. It's multiplied by A. So let's take it over by dividing. I get D minus VIT over 1/2 of T squared. This is especially ugly, but it works. A is equal to displacement minus VIT over 1/2 T squared. Let's take a look at another one. VF squared equals VI squared plus 2AD. I want to solve for, well, let's solve for VF first. This one's simple. We're just going to say VF is equal to the square root of VI squared plus 2AD. It's almost by itself now. We just have a square there. We got a square root to get rid of that. So VF is equal to VI squared plus 2AD. Let's solve for VI. Remember what the rule is? Get rid of what is attached to the VI. Well, there's nothing attached to the VI. So then let's get rid of what is not attached to the VI. What isn't attached? Well, that would be the 2AD. Let's take it to the other side by, well, because it's added to VI squared, let's take it to the other side by subtracting. Now, so I want to solve for VI. All we're going to do is square root this to get VI by itself. I get VF squared minus 2AD. The opposite of square is square root. So VI is equal to the square root of VF squared minus 2AD. Let's use the same equation to rearrange one more time. This time, let's solve for A, the acceleration. What's not attached? Get rid of what's not attached. What's not attached? VI squared. It's not attached to the 2AD. So let's take it over to the other side by, well, it's added to 2AD, so let's take it to the other side by subtracting. VF squared minus VI squared equals 2AD. Remember, we're still solving for A. Now get rid of what is attached to the A. Well, that would be the 2 and the D. They're multiplied by A, so we're going to take those to the other side by doing the opposite of multiplication, which is division. VF squared is minus VI squared over 2D is equal to A. Now, I'm not going to show you any more right now, but the rules of rearranging any equation are the same as what we've just done for the last several examples. 1, get rid of what is not attached. If it's not attached, it's going to be added or subtracted. Take it to the other side by doing the opposite. If it's added, subtract it from the other side. If it's subtracted, add it to the other side. Then get rid of what is attached. If it's multiplied, attached by multiplication, then take it to the other side by division. If it's attached by division, then take it to the other side by multiplication. We got a few examples for you here today. We'll go through these examples and then we'll set you to work on some questions. The first example, example number 8, this is in your notes, page 6, says a car traveling at 10 meters per second accelerates to get past another car. If it speeds up to a velocity of 25 meters per second in a time of 6 seconds, what's the acceleration of the car? First, I want you to recognize that this problem involves acceleration. That means it's a group B problem. Which equation am I not allowed to use? V equals delta D over delta T, because it's for constant or average velocity only. This is a group B equation. I'm going to use one of those acceleration equations that I just learned about. Let's write down my givens, and then let's see which one seems to fit the best. A car traveling at 10 meters per second, that's going to be my initial velocity. This is what it's going when this problem starts. It accelerates. It speeds up to a velocity of 25. That's going to be my final velocity. That's how fast it's moving at the end of the problem. In a time of 6 seconds, we're going to say delta t, the time interval, is 6 seconds. We want to find the acceleration. VI, VF, T, and A. We're allowed to use any of these equations, any of these group B equations. But let's see which one fits the best. VI, VF, A, and T. I want to try the first one, I think. Let's try the first one. If it doesn't work for me, that's okay. We'll try another one. As long as we're not trying V is equal to delta D over delta T, we should be good. Delta V is VF minus VI. VF is 25. VI is 10. T is 6. 25 minus 10 is 15. 15 divided by 6 is 2.5 meters per second squared. Sure enough, it worked. We got the acceleration by using the base equation for acceleration. Let's try number 9. This one says, how far has the car in example 6 traveled during its time of acceleration? We still have all the givens that we had in the last question. VI, VF, T, and now we have A as well. We want to know how far it travels. Let's try this one. VI was 10 meters per second in the last question. VF was 25 meters per second in the last question, over 2 times the time interval of 6 seconds. 25 plus 10 is 35, divided by 2 is 17.5. 17.5 times 6 is 105 meters, but we're actually going to round that to 2 digits. We have to put it in scientific notation to do that. We get 1.1 times 10 to the 2 meters. So it accelerates at a rate of 2.5 meters per second squared, and it covers a displacement of 1.1 times 10 to the 2 meters in the process. Now, In this case, this equation is not the only one that'll work for this. We could try maybe d is equal to VIT plus 1/2 AT squared. We know VI, we know T, we know A now from the previous question, we know T. That'll work. D is equal to VFT minus 1/2 AT squared. That'll work as well. We have VF, we have T, we have A from the last question. That'll work as well. Don't be afraid to try one. Look, if you see a problem involving acceleration, a group B problem, try one of the blue equations. Sometimes there's more than one that'll work. But if you try one that doesn't work, then just try another one. Okay, I want to do example number 10 now. It says a rock falls from a height of 50 meters above the ground. What's the speed when it strikes the ground? Let's assume that it falls from rest. If it falls from rest, VI is 0 meters per second. It's dropped. It's not moving until after it's dropped. VI is 0 meters per second. The displacement here, be careful. The displacement of this rock, it falls 50 meters. So the displacement will be 50 meters. We're going to make it negative because it falls down 50 meters. It ends up below where it started. One more thing that we have here, although it doesn't say it in the question, what's the acceleration? How quickly is the velocity changing in this question? We saw earlier that anytime an object rises or falls and is under the influence of just gravity, A will be negative 9.81 meters per second squared. We're looking for VF here. Look, I can try this equation. It's a group B equation. This is a group B problem. This is a group B equation. I can try this one. But guess what? I can't solve for VF. That's okay. I try again. Maybe I say VF squared is equal to VI squared plus 2AD. I have VI, I have A, I have D. This one looks like it's going to work. We're going to say VF, get rid of the square sign there by square rooting, is equal to VI squared plus 2AD. VF is equal to, VI is 0 plus 2 times negative 9.81 times negative 50. Let's do this one on our calculator to make sure that we can all plug it in properly here. We're going to say 0 squared minus, let's put all that stuff on the right-hand side in brackets there, 2 times negative 9.81 times negative 50. Gives me negative 981. Now let's square root that. Second function, square root. Second function, answer. Typo there. Let's try that again. 0 squared plus bracket 2 times neg 9.81 times negative 50. Positive 981. Let's square root that. Second function, square root. Second function, answer. I get 31 meters per second. The speed, not the velocity, the speed of this rock as it strikes the ground just before it hits is 31 meters per second. Remember, when an object rises or falls and only gravity is affecting it, let's make A negative 9.81 meters per second squared. And finally, the last example that I want to give you here today, example number 11, says a ball rolling down a hill accelerates at a rate of 3.0 meters per second squared. If it initially moves at 5 meters per second, how far will it travel in 10 seconds? This is a group B problem, again, because it involves acceleration. In other words, we can't use V equals D over T. You can use any one of those 5 acceleration equations, however. For this question, we're going to say VI is 5.0 meters per second. We're going to say the acceleration of this ball is 3.0 meters per second squared. We're going to say the time interval is 10 seconds, and we're looking for delta D, the displacement. Let's say delta D. Let's try this one. VIT plus 1/2 AT squared. Remember, you're probably not going to be as quick at figuring out which equation to use as I am. That's okay. Try one. Go with it. If it doesn't work, then try another one. If it doesn't work, try another one. There's only 5. Sooner or later, you've got to find the right one. VI is 5.0 meters per second. T is 10 seconds. Plus 1/2 of A, which is 3.0, times T squared, which is 10 squared. 5 times 10 is 50. 10 squared is 100, times 3 is 300, times 1/2 is 150. So we have 50 plus 150, which is 200. Now, technically, this is a 2-digit answer. Okay, this is 2 digits, 2 digits, 2 digits. That means my final answer is going to be 2.0 times 10 to the 2 meters. Now, what I would like you to do is have a look at worksheet number 4. We've skipped a couple worksheets. We'll go back to them. I want you to look at worksheet number 4. There's 13 questions on that worksheet. Some of them are going to be challenging. Remember, these are Group B problems. Use the acceleration equations, the one that we just learned today. Try one. If it doesn't work, try another one. If it doesn't work, try another one. Write down your givens. Keep trying equations from the Group B list until you find one that works. If you have to refer back to your notes to see how to rearrange an equation, do that. If you have to rewind this podcast to see how to rearrange an equation, do that. Do your best today and tomorrow at worksheet number 4, questions 1 to 13.